Welcome. In this lecture, we discuss what is the Lagrange's linear equation. So yesterday, we obtained the Lagrange's equation by partial differential equation. So what is the definition of Lagrange's linear differential equation? So an equation of the form PP plus QQ is equal to R. So this is the Lagrange differential equation where P, Q, R are the functions of x, y, z is called a Lagrange's equation. So we know that the arbitrary function phi of u is equal to 0. Phi of u is equal to 0, where u and v are functions of of x, y, and z. So this is the arbitrary function. Something phi of u is equal to 0. And we eliminate arbitrary function. Yesterday, we eliminate arbitrary function and obtain the partial differential equation PP plus QQ is equal to R. Okay? So this is the differential equation. So this is, again we write here this differential equation, that is PP. So we obtain by eliminating arbitrary function phi. So we have here, so what happened? So that is PP plus QQ is equal to R. So this is equation number 1 over here. So this is equation number 2. So by eliminating the arbitrary function from phi of u is equal to 0, we obtain the Lagrange's linear equation. So we discussed about that yesterday. So what is the Lagrange differential equation and how to obtain Lagrange differential equation by from phi of u v. So eliminating the arbitrary function phi. Okay, where p upon, so we yesterday discussed about that. So what is the p upon dou u v by dou yz. So we know that. What is q? Dou u v by dou zx and r upon dou u v by dou xy. So we know that. So we discussed about this in the last lecture here. So that is p upon this, q upon this, r upon this here. Okay. So this is equation number 3. So these equations can also be obtained from the equations p dou u by dou x plus q dou u by dou y plus r dou u by dou z is equal to 0, and p dou v by dou x plus q dou v by dou y plus r dou v by dou z is equal to 0. Okay, so this can be written as equation number 4. So these equations, if we solve these equations, we get again this. So this is a Jacobian. We write this in determinant form. This is determinant. And if we solve this equation for PQR, we solve these two simultaneous differential equation. So we get also same this. So Let us consider, let us consider, let us consider the equation. Let us consider the equations. Something u is a function of, so x, y, z is equal to something a, and v is also a function of x, y, z having arbitrary constant b, a and b are the arbitrary constant. So this is the arbitrary function here. So u is a function of x, y, z, v is a function of x, y, z, u is a function of x, y, z, a and b are arbitrary constants. Okay, so this is equation number 5. This is equation number 5. So differentiate equation 5, we get 5. We have. So we now differentiate this equation. So what is the total differential of this equation and this equation? So this is very simple here. So that is du is equal to dou by dou x into dx. Differentiate this with respect to x, y, z. So that is dou by dou y into dy plus dou by dou z into dz is equal to 0. Okay. So again we obtain the differential of this with respect to x, y, z. So what is this? So dv is equal to dou v by dou x into dx plus dou v by dou y total differential dy plus dou v by dou z into dz is equal to 0. So this is equation number 6 here. Okay. So these are also equations we obtain from after taking differentiation of this equation. So we get this. So solving these two equations, solving for dx, dy, dz, we get. So solving this equation for dx, dy, dz. So we get dx upon. So dx upon what? Dx upon. So that is dou uv by dou yz. Dou v by dou yz or something determinant here. So what is the determinant? Dou u by dou y, dou u by dou z. So okay, just we write determinant here. Okay, what is the determinant? Dou u dx upon dou u by dou y, dou u by dou z, dou v by dou y, dou v by dou z. Okay, this is determinant. So what is this? This is this Jacobian here. This is Jacobian. So what is this? So this is Jacobian here. So we write simply here this Jacobian. So that is dou u by dou yz. So this is this. So we write directly. So dou u by dou yz is equal to dy upon. Similarly, we get here this. So solving this equation for dx, dy, dz, we get dou uv by dou zx. Again, dou z upon dou uv by dou x, dou y. So this is equation number 7. So we obtain, so we taking here the function u is a function of x, y, z, v is a function of x, y, z, and differentiate these equations, we get these equations, and solving that equation for dx, dy, dz, we get the same equation. Okay, and also we obtain from this equation, from this function, we obtain this equation. Okay, so comparing this equation and this equation, by comparing equations 3 and 7, we get what happened? So we compare this equation and this equation. So this is same here. So denominator is same, this is same, this is same. So what happened here? So this is a dx upon p. Dx upon p is equal to dy upon q is equal to dz upon r. Okay? dz upon r. So what is this? This is ordinary simultaneous differential equation. So this is ordinary simultaneous differential equation. Okay. So we solve this differential equation by usual method, taking fractions or taking multipliers. We solve this differential equation. So we get solving equation 8, we get here two solutions. So two solutions. We already solved these equations, ordinary partial differential equation, and taking examples. So taking first two fraction or taking any fractions or taking multipliers. So we obtain two solutions, two parts of the solutions. So solving equation 8, we get, so that is u of xyz is equal to a arbitrary constant here, and v of xyz is equal to b. Okay, so solving this equation, we get this here. So what is the general solution of this differential equation? Lagrange linear differential equation. Therefore the general solution is what happened? So this is phi of v is equal to 0. So this is the solution of the Lagrange's differential equations. So this is a pp plus qq is equal to r here. So what is the theory here? Simple. So this is linear differential equations. So we obtain this linear differential equation by this function phi of u is equal to 0 by eliminating arbitrary function. So we already discussed. So we write same part here of the previous lecture. So like that. So we differentiate this again with respect to xy. So we get this equation, and solving this equation for dx, dy, dz, we get this. Comparing both equations, we get this equation. This is the ordinary simultaneous differential equation, and we obtain the solution of this equation like that. So this is the general solution of phi of u is equal to 0, the solution of this differential equation. So we discussed the theory, how to solve the Lagrange differential equation, linear differential equation. So we take an example. So what is the example here? Solve example. Solve y square z upon x into p plus xz q is equal to y square. Solve this differential equation. So this differential equation, this is a linear differential equation of the form. So pp plus qq is equal to r. So comparing the given equation with the Lagrange equation with pp plus qq is equal to r, we have. So what happened here? So what is p? P is what? Comparing both equations, p is equal to y square z upon x. What is q? Q is equal to xz. What is r? R is equal to y square. Okay? Then, what is Lagrange's auxiliary equation? Therefore, the Lagrange's auxiliary equations are. So what are the Lagrange auxiliary equation? So we discuss in the theory. So that is dx upon p is equal to dy upon q is equal to dz upon r. So these are the auxiliary equations of this Lagrange equation. P plus q is equal to r. So put p is equal to this. So dx upon. So we just discuss in the theory. So what is p here? So that is y square z upon x. What is q? So dy upon xz. What is r? dz upon y square. So this is a ordinary simultaneous differential equation. So Lagrange auxiliary equations are ordinary simultaneous differential equation. So we solve this differential equation by usual method. So taking first two fractions or first and last fraction, taking first and last fraction, we have, what are the fractions here? So that is dx upon y square z upon x. So what is it? dz upon y square. So what happened here? So this is y square get cancelled. So this implies that y square get cancelled. So z is here, x is here. So x dx is equal to z dz. So this implies that x dx minus z dz is equal to 0. So on integration we get. So on integration, so what happened? X square upon 2 minus z square upon 2 is equal to c1 upon 2. So that is integrating constant. So 2 to get cancelled. So that is x square minus z square is equal to c1. So this is one part of this solution here. So this is one part of the solution. So what is the next part? Taking first and last fraction. First and taking, or you take. So what happened? Taking first two fractions. First two fractions. So what happened? Taking first two fractions. So that is dx upon y square z upon x is equal to dy upon x square. Okay? So what it implies? So y square is there. Y square. Okay? So what it implies? So this is, I think, dx dy xz. So what happened here? Z can cancel. So this is what happened here. So x here, x square dx, and then y square. Z cancel. Z cancel. So y square dy. Okay. So therefore, x square dx minus y square dy is equal to 0. So on integration, taking integration of this equation, so what happened here? So that is x cube upon 3 minus y cube upon 3 is equal to something integrating constant c2 upon 3. So this is equal to x cube minus y cube is equal to c2. So this is another part of the solution here. So this is another part of the solution. So this is equation 2 here. Okay. So what is the general solution of this differential equation? So therefore the general solution is what? Phi of uv is equal to 0. So what is u? U is this. What is v? V is this. So this is a phi of x square minus z square and x cube minus y cube is equal to 0. So this is the general solution of the given partial differential equation. Okay, so how to solve this Lagrange linear equation? So this is a very simple one. So we take another example here. Simple example. Solve yzp plus yzp plus 2x cube is equal to xy. Solve this differential equation here. Okay, so this is the Lagrange linear differential equation. So comparing the given equation with this pp plus qq is equal to r, Lagrange equation. So comparing these equations, we get what is p? P is yz. What is q? Q is 2x. Q is 2x. What is r? R is xy. R is xy. Okay. Therefore, the Lagrange's auxiliary equation of these equations are dx upon p, dy upon q is equal to dz upon r. Okay. So what is p? P is what? Yz. So this implies that here. P is yz. What is q? Q is 2x. What is r? R is xy. Very simple. Okay. So this is the ordinary simultaneous differential equation. Okay. So how to solve this differential equation? So taking first and last fractions. Okay. Taking first and last fractions. So what are the first and last fractions? So that is dx upon yz is equal to dz upon xy. Okay. So y get cancelled. So what happened here? So this implies that x dx is equal to z dz. So this implies that x dx minus z dz is equal to 0. Okay. Taking integration of this. So on integration we get, so that is x square upon 2 minus z square upon 2 is equal to c1 upon 2. So 2 to get cancelled. So we get the first part of this solution here. So that is x square minus z square is equal to c1. So this is first part. So what is the second part? To find the second component of the complete solution here. So taking last two fractions, this and this, taking last two fractions. So what are the last two fractions? So that is dy upon 2x, dz upon xy. So what happened here? X get cancelled. So this is y dy 2 dz. So this implies that y dy minus 2 dz is equal to 0. So taking integration of this. So what is the integration? On integration we get y square upon 2 minus, that is 2 as it is, derivative integration of dz, that is x. So this is something is equal to c2 upon 2. So multiplying 2 throughout. So this implies that y square minus 4x is equal to c2. So this is the another part of the solution here. Therefore the general solution is so what is the general solution of this equation? So that is phi of uv is equal to 0. So what is u? U is this. So this is pi of x square minus z square. What is v? So y square minus 4x is equal to 0. So this is the complete solution of this, or general solution of this given differential equation. So this is a very simple differential equation. So we compare that differential equation to the Lagrange equation, and we write those equations in the auxiliary form here, and we solve by usual method, as we already solved the ordinary simultaneous differential equation. So we stop here. We're taking another examples in the next lecture. Thank you.